So continuing our discussion with dilations and how we can transform figures, we're going to take a look at what happens when they're on the coordinate plane today. So maybe a little bit of a review. We know similar figures are figures that are in the same shape, but not necessarily the same size. That's to say that one would be a dilation. So something kind of to keep in mind here is if for some reason the figures should also be the same size, we would call them congruent, meaning we'd have a dilation of 1, not changing anything. Okay, so we see here similar triangles. ABC has been scaled to triangle EDF. So I could look at this and say, here's our pre-image, and this would be our image. And it wants to know what's the scale factor. In other words, how much bigger is our image? And this example may be easy to see just based on the numbers. It looks like the image is twice the size, but maybe if the numbers aren't as big, how would we do this? So I would take my pre-image and I would say, all right, well, if I know I'm starting with 10, it looks like there's got to be some factor meaning multiply, that would give me that corresponding side of 20. And if I were to solve for k and divide through, I could find that k would equal 2. And a good check, I should be able to do that for each side. So if I did the same thing for 6, that corresponding side is 12. And again, I could see there k would be 2. And I could do it again for my last side, 7. And that corresponding side is 14. And again, I can see my scale factor is 2. So the operation that we use with dilations is always going to be multiplication. Okay, symbolically or as a rule, again, I can see capital letter D for dilation. The O is telling you the center, and in this case, it's going to be the origin for today. And that R is your scale factor. So if I'm looking at the coordinates x, y, and I'm thinking multiplication, my new coordinate would be x times my scale factor of r, comma, y times my scale factor of r. Okay. So we're going to see how this works with just some basic coordinates here, constantly thinking of multiply. So for here, for 1a, I have 5, 3 is the coordinate with the scale factor of 3. So if I'm thinking 5 times my scale factor, and then 3 times my scale factor, that's going to give us a new coordinate of 15, 9. Okay, for our second example, again, scale factor of 7. So I want to think my coordinate times the scale factor, coordinate times the scale factor. It's going to give us a total of negative 14, comma 0. Same thing if we have a fraction, it works the same way. And we're going to see what happens when we have a fraction, graphically speaking, later on. So process doesn't change, so we're still multiplying. So 9 times 1/3, I'm going to get 3. Negative 6 times 1/3, I get a negative 2. Okay, and one more example over here. So I have 5 times my scale factor of 1/2, negative 8 times the scale factor of 1/2. You're going to notice this first coordinate, that's going to give us either a fraction or a decimal. It's either 5/2 or 2.5, and comma negative 4. So don't freak out if you get a fraction. Fractions or decimals, they're numbers too. Okay, now it says we have to determine if it's a stretch or a dilation. So keep in mind, up above we said a dilation, we had one number, one scale factor, and it multiplied both the x and the y, and that number, same number. That gave us a dilation. If the numbers are different, such as this first example in A, I can see I'm multiplying x by 2 and y by 5. Well, now it's not a dilation. I've still changed it, I've still transformed it, but it's not a consistent transformation. So I would have to call that a stretch. So why would I call it a stretch? I would just say my scale factor for the x and y coordinates are different. And they should be the same if it's going to be a dilation. So if we look at letter B, we're multiplying x by the square root of 5, y by the square root of 5. So that's the same scale factor that's going to give us a dilation. Okay, our explanation, kind of like what we said, same scale factor. And we're thinking for both x and y coordinates. Okay. What if they've given us the point? So 3 is kind of taking a look and saying, well, I already know the start, I know the finish, I know my pre-image and I know my image, but how did I get there? Right, well, if I'm thinking again in terms of multiplying, since our dilations are multiplying, thinking, so I'm starting with -4, I have to multiply that by something in order to get -16. Okay, so I could solve for k. I could say, well, k in this case is 4. Now, because it's a dilation, your check would be to do the same exact process with your y coordinates. So if I solve, again, I'm going to find 4, and so that's telling us our scale factor for this problem is 4. Okay, on the back, what happens if we get now a composition? Well, same thing that would happen before if we did a composition. First off, you want to think order. This is huge. We're going to work backwards. We're doing that reflection over the x-axis first, and then we do our dilation. Okay? So I would always tell you, make sure that you're writing this out so that you can see that actual transformation. This will also give you some partial credit. Okay? So if we are going to transform this first thing that we're going to do is a reflection over the x-axis. And if I'm thinking reflection over the x-axis is party, that means y has to change. So that's going to bring us to a +5. Now we're going to take this and do our dilation. So I have a dilation centered at the origin, scale factor of 2, meaning I'm going to take each coordinate here and I'm going to multiply it by 2. So I'm going to have 8 for my new x value, and I'll have 10 for my new y value. And as we're moving on. So we know dilations map line segments to a parallel line segment, meaning same slope, of a scale factored length. Okay, assuming the center of dilation is not on the line segment. So this is kind of big here. We talked about this last time. This was from our last section of notes, so this is just kind of a reminder. When you're doing dilations, we get parallel line segments, so you want to keep that in mind, thinking same slope. So for this next one, we have a line whose equation is, it's dilated with a center at the origin by a scale factor of 1/2. So now we have to come up with a new equation of this line, and they're asking for this in slope-intercept form. Okay, so first thing I would do is I would take this equation, and I would solve, and let's get it into that slope-intercept form, that y equals mx plus b. So I'm going to move that 5x over, so subtract that over, I have a -5x plus 12. And we want to get y by itself, so I'm going to divide everything through by 3. So now I have y is equal to -5/3 x plus 4. Okay, so things that I could pick out from here. From here, I know that -5/3, that's my slope. So the slope of this line is -5/3. Since we just set up above, if I'm going to do a dilation, it has to be parallel. So I know my new slope has to be the same thing, and it's still going to be a -5/3. So that's something we want to keep in mind. Your new slope is the same as your original slope. Okay. What we're going to do is just stop there for a second. Let's go over to our graph and let's see what our first original equation actually looks like. This -5/3 x plus 4. So I'm going to darken in our axes just so we can see where we're at. And if we start graphing this, keep in mind we know that that is your y-intercept, meaning that's your starting point. So I'm going to go up 4 on the y-axis and put a point. Then I'm going to graph a slope of -5/3, meaning I'm going down 5 and I'm going to the right 3. I'm going to put a point. I'll do that again. Down 5 and right 3 and put a point. We can also, back at the y-intercept, go up 5 and to the left 3 and put a point. And now with a straight line, if we were to connect these dots, and I just erased that one. Okay, so let's try this again. So this is why I use my marker typically, and my lines are not straight. I apologize, but we're going to just kind of go like so today. Make sure to label it. So here's y equals negative 5/3 x plus 4. Okay. So we know the new equation that we're going to make has to have the same slope. So what do I do? Okay, well, let's think about this. This y-intercept, that's a coordinate. Just like we did with all those other coordinates on the front of the page. I could take that coordinate and I could say, well, that's my location 0, 4. But our scale factor here is the scale factor of 1/2. So if I did a dilation centered at 0 with the scale factor of 1/2 on the coordinate 0, 4, my new location, multiply everything by 1/2, would be 0, 2. This is your new y-intercept. Okay, so I could write that equation now. I have everything I need. They wanted it in slope-intercept form. I have my slope, I have my intercept. So our new equation, put it all together, negative 5/3 x plus 2. Okay, so if we go back to the graph and we try and graph this one. So I'm starting at my y-intercept. This time we said it would be 2, so I'm going up 2 and I'm putting a point. And I have a slope of negative 5/3. So again, down 1, 2, 3, 4, 5 over 3, down 5, and we're going to fall off the graph and go over 3. You can also start at the intercept and go up 5. 1, 2, 3, 4, 5, back 3. And again, since our board's acting up, I'm going to try and make this as good as I can. We see that that's going to be parallel. I can label this equation. So here's my negative 5/3 x plus 2. They're parallel. And I can see, since it was a scale factor of 1/2, it got smaller. Really, a line gets smaller? No. What happens in this case is because our center is at the origin, scale factor of 1/2, if you think back to our last note sheet, it's going to move it closer to that center of dilation. So I can't really say the line gets smaller, lines don't end, but I can say it gets closer to the center of dilation. Okay, so we don't always have to graph these. If we understand what's happening there, here we have a same kind of problem. It's going to ask us to write a new equation. So it says line L is mapped onto M by a dilation centered at the origin, so this is good, and we have a scale factor of 2. So the equation that we're beginning with is 3x minus y equals 4. So we have to find this new equation with a scale factor of 2. So just like we did the last time, I want to solve and I want to get y by itself. So I'm going to move the 3x over. So we have a negative y, watch your negative, equals negative 3x plus 4. And I want to get positive y, right? So I'm going to divide everything through by negative 1. So that means y is equal to, here's a positive 3x minus 4. Okay, so from this equation, I know my slope is 3. So that means my new slope has to be the same because we know they're going to be parallel. And then this negative 4, that's your y-intercept. So let's write that as a coordinate. Okay, so as a coordinate, your y-intercept looks like 0, negative 4. But we need to do a dilation centered at the origin with a scale factor of 2. So that means 0 times 2 is 0. Negative 4 times 2 is negative 8. So now this is my new y-intercept. And if we put this all together for an equation of a line, thinking mx plus b, I have y equals mx plus b. Here's your new equation. So we'll practice some more of this in class. Hopefully this was a good beginning. Don't forget to like and subscribe. Have a great day.